Now we'll continue our review of weather. And so we want to review density altitude for just a moment. Remember that temperatures going up, the warmer it is, along with the pressures going down, means that the density altitude is increasing. And with increased density altitude, we have less performance for our airfoils, and also for the motors as well. I mean, but at any rate, that's the major factor in density altitude, and that's the definition of density altitude. The higher the temperatures and the lower the atmospheric pressure, the higher the density altitude, the less performance. And the reciprocal, of course, with temperature going down or pressure going up would increase our performance as well. And of course, we just remember about the standard levels. Standards for pressure is 29.92 or 1013 millibars. Normally in the US we use 2992. That's a number you just have to memorize. And there's a typical question for density altitude on the FAA written knowledge exam. What is the standard temperature and pressure value for sea level? Yeah, A, 15 degrees C and 29.92 inches of mercury. There's the conversion factor as well, if you want to convert from Fahrenheit to C, either way. All right, and here's another sample question. If the outside air temperature, OAT stands for outside air temperature, at a given altitude is warmer than standard, the density altitude will, and this is, I'm trying to determine whether you understand the whole concept, density altitude will be higher than pressure altitude. Pressure altitude is 29.92, and as you increase the temperature, right, you all know that, just to review. Temperature is above standard, density altitude will be higher than the pressure altitude. That's in the Pilot's Handbook of Aeronautical Knowledge. That's the reference. And many other places as well, also in AC 00-6. All right, so again, this can't be overemphasized, I believe. High density altitude means less performance. High density altitude occurs when the temperature goes up and or the pressure goes down. So if the pressure goes down, the air is thinner, higher density altitude. Or if the temperature goes up, it's higher density altitude. And then when you get both together, it's even more higher. And the chart, recall, we had I think it was last lesson or the lesson before last, a really good video that we got to watch that tells us how to work through this chart. Remember, again, I will just remind you that we work our way over here first, and we're trying to find out this number. We're trying to find out what the pressure altitude is first, so we go to the altimeter setting, whatever we get on the radar, on the weather report. Of course, in the FAA questions, they will give you an altimeter setting, and so then you find the conversion. Let's say it's 29.00, then that's it. And of course, they don't mention it, but this is obviously is plus 863, or if it's down here. So this is thinner air, and this down here, because it's minus, thicker. Okay, so that's sort of how the proportion goes. But anyway, you find out from the altimeter setting, and you find out what altitude you're at, the airport elevation, or wherever you're at, then you either subtract or add that from your actual sea level altitude to come up with the pressure altitude. Then you work the chart. Then you find whatever temperature they give you. If it's 21 degrees centigrade, you find the right one. 21 degrees is here. So then you go up from here to wherever, and then go over, and that's your. Okay, I'm not going to go any further than that. So you need to go back and look at that other video if you're having struggles with this. But you just want to be able to do this fairly efficiently. You don't have a whole lot of time to sit there and work through this chart, so you sort of want to know how to do it before the test. And here's a question, a more general question about this same issue. Which factor would tend to increase the density altitude at a given airport, referenced in a weather briefing? Increased density altitude is the question. Read the question. Read the question. What tends to increase the density altitude? An increase in barometric pressure? No, that means the air is thicker. A decrease in relative humidity? Actually, we've talked about that before, but relative humidity is a factor. The higher the relative humidity, the less thin. So a reduce would actually decrease. So it's got to be A, or B rather, increase in ambient temperature. And that actually is pretty obvious. Warmer it is, the higher the density altitude. Right. Oop, there we go. Hot day air becomes thinner and lighter, and its density is equivalent to a higher altitude in the standard atmosphere. Thus the term high density altitude. And that's from the Weather Advisory Circular, AC 00-6. And a review of this whole concept of warmer air rising, these air parcels that are warmed by uneven heating of the Earth's surface. And as they rise, if they're warmer than the air around them, they will rise. And as the air packet rises, it starts cooling off. Somewhere around 5.5 degrees of temperature drop per 1,000 feet. When you get to a certain altitude, the air is cooled to the point where it is saturated with moisture, and that moisture can no longer be suspended as water vapor, and it turns into some sort of a cloud. That's the saturation point, or the dew point. We normally call it a dew point. It can be reached in two different ways. It may just be an addition of moisture until it reaches the maximum amount of moisture that can be held at that particular temperature. Or we can cool the air to the point where the moisture can no longer be suspended, can no longer contain that moisture. Saturation, therefore, is reached through evaporation or condensation. Either way, saturation occurs, the moisture becomes visible water droplets as fog or clouds, whatever. So for an example here, as a general rule, we know that if the air is relatively dry, the temperature drops somewhere around 5 degrees Fahrenheit per 1,000 feet. So we could right now call the Griffin Airport AWOS, we've got the phone number available, and obtain the current weather, which would include the temperature and dew point. From those two numbers, we ought to be able to predict how high above the ground the air will start to condense into clouds. And you could do that. You could take a pretty good guess about where the clouds will occur, depending on wind velocity, a lot of other things that might affect that also. On a relatively moist day, though, the temperature drops around 3.3 degrees per 1,000 feet. So those some numbers let us figure out the different cloud altitudes. So they're not perfectly uniform, of course. All right, high-level clouds. Want to just be somewhat aware of these clouds. Different types of high-level clouds. There is a cirrus cloud, and generally it's just a high-level cloud, thin, obviously white in appearance, although with the sun shines the right way, it's consisted partly of ice crystals, and it can be very colorful at times. So we have cirrocumulus clouds. They're just these very high cumulus, and cumulus, of course, is the Latin for built up, bumpy kind of thing, so it's somewhat lumpy, but high level still. And then cirrostratus, stratus being flat and level, they're high level clouds. Then we have these mid-level clouds, altocumulus, altostratus, and nimbostratus. Altocumulus are cumulus, remember the word sort of bumpy, just you want to think about that, bumpy sort of clouds. High level, though, at mid altitudes, not high altitudes. And then we, of course, have altostratus, which is a mid-level stratus cloud. As you get closer to a warm front, you'll get some of this. And then nimbostratus. Nimbo is rain, right? So flat clouds that are emitting some kind of very light mist or some kind of precipitation. We have these four kinds of low-level clouds. Cumulus, the typical clouds that you see pretty much every day around Georgia, um, except if there's some kind of frontal activity nearby. Then we have the cumulonimbus, which you can see nimbus being rain, as if there's enough vertical development in these clouds, we'll end up this moisture rising high enough to condense into actual rain. Then we have stratocumulus, which are low-level flattened clouds. And oh no, I made a mess there, didn't I? I'll erase that. Then we have this stratus, which is like a typical overcasty, wintry day, will consist of stratus clouds. All right, and there's the classification you might want to take a look at, think about. There's some other peculiar names. Chances are these won't be on the test, except for the cumulus, stratus, and cirrus. Those are the main types that you just sort of need to know. Cumulus being heaped or piled up, stratus formed in layers, cirrus little fibrous clouds, high-level clouds usually. There isn't a good example of a cloud here. What's happening is the air, I think this is Japan, the air is pushing up the side of this hill, and as it gets higher it turns into visible moisture, right? So then we have fog. The FAA does ask a number of questions about these different kinds of fog. You need to be aware of them. I'll try to make it as simple as possible, and of course remember this is review and you are responsible for your own self-study. But anyway, fog simply forms again as water vapor, as the air reaches a saturation point where it can no longer hold the moisture. And we call it a dew point. In aviation, we call it dew point. The Weather Channel, they'll call it humidity, the level of humidity, sure. And of course, we talked about that before. You can reach this in two ways. Either you add moisture to air to the point where it can no longer hold it, or you take air that has moisture and you cool it and to the point where it can no longer hold that air. Those things are important to remember. So we have these three different kinds here: radiation, advection, upslope. Radiation fog is basically the kind of fog that's produced over a land area when the sun goes down. The ground cools off fairly rapidly, and that cooler ground cools the air above it, of course, and it reaches the point where it can no longer contain the moisture, right? When you cool air that's moist, eventually, perhaps, in the case of radiation fog, definitely, that's when the air can no longer hold the moisture. So it turns into fog. Yeah, so it's over the ground. Got relatively moist air. Clear skies often is what you need, which is interesting because when the sun goes down, you would think that that would hold the heat goes off into space fairly rapidly. So the depiction there on the chart is probably all you need to know. I'm probably over talking about it, but you can't have much wind in radiation fog. If there's a little bit of wind, it mixes the air and it will not form fog. Advection fog, on the other hand, does require some air movement, just some wind. Okay, in fact, it can have up to 15 knots of wind. And basically, what it's doing is, as you can read in the diagram, you can read yourself, I suppose. But warm moisture moves over a colder surface, and as that temperature drops, it turns into fog. So it could be very cold water, or it could be air over the water moving over a colder land mass to form this kind of fog. Advection requires some wind. Moist air moving over a colder surface. As the air is cooled over this colder surface, it reaches its saturation point and can no longer hold the moisture. Then we have upslope fog, adiabatic cooling caused by forced the air being forced up, right? The wind is blowing this way. Again, we need wind for this. Those are the two things for advection fog and for upslope fog, we need wind, some amount of wind. And again, that's maximum 15 knots of wind. Anything more than that, it mixes too rapidly. But as air rises, it cools and reaches its saturation point, and then you end up with fog. Upslope fog is pretty dense, and it can go to fairly high altitudes. We might be able to make an argument that that picture of Mount Fuji, the Japan picture we saw a little bit earlier, that might have been a form of fog, possibly. And that might be true. So here's a question. What type of fog depends on wind in order to exist? We talked about it already. It'd be advection fog and upslope fog. So that one right there. Now let's talk about precipitation here. We've talked about fog. Let's talk about precipitation. There's some rules that you want to remember, that precipitation all have some common ingredients. One, of course, is that you have to have water vapor. I mean, perfectly dry air. You don't get rain in the desert, okay? And sometimes at the North and South Pole, when it's extremely cold, there's no moisture either in the air, but that's beside the point. You need water vapor. You need sufficient lift to condense the water vapor into the clouds to get rain, especially. And that's what precipitation is, basically a fancy word for rain, or snow, or sleet, or hail, or ice pellets, or all of those things. But so in these cases, we need water vapor. We need sufficient lift to condense the water vapor into clouds. In other words, lifting force, something lifting them. And then you got to have a growth process, because if the atmosphere was perfectly pure, there would be nothing for these water droplets to cling to. So you need a growth process that either a lot of updrafts to keep these moisture droplets suspended long enough to freeze into hail or sleet or whatever form, and also for even just the raindrops to turn into rain, right? Because you've been out there before and there's just a very light mist. It's sort of like, it's not really rain. It's just sort of like a thick fog kind of stuff. Okay, so you need some of that to turn into these things: rain, snow, snow grains, snow pellets, hail, freezing rain, sheet, sleet, ice pellets, ice crystals. This is an example of that growth process here. Not all clouds turn into rain, right? Or some kind of precipitation. So obviously, you look out there and there's clouds all the time, and usually too small. These rain droplets are too small or light to fall to the ground. Interesting enough, the average time it would take for a cloud droplet to fall to the ground from like 3,000 feet might require several days. And lots of times it evaporates before it hits the ground. So somehow there has to be a process where these things grow in size to the point where they can actually are heavy enough to actually fall. That's one of the major factors in a thunderstorm, is that it has so much uplifting and downdrafts, so much turbulence, that it suspends these droplets for a long time. So they freeze, they come down, melt a little bit, then they go back up and freeze some more, and they get layers. If you take a hailstone and look at it carefully, even if you crack it in half, you can see it's full of layers. So we've got a couple of videos, and I'll be down in the description below are the links to these videos that I think will be really helpful. There's one from National Geographic that sort of gives an overall picture. Then as a more specific video, the second video talks about the stages of thunderstorms, and we're also going to talk about that, but it wouldn't hurt to watch both. But the review here will cover that. So here's what's necessary for a thunderstorm. You must have these things. You must have water vapor. You must have some kind of unstable air, and you have to have a lifting force. Something has to initiate the lifting force. It may be the uneven heating of the air. It may be a mountain. It could be some kind of rising terrain that, as the air blows across, it starts that air starting to move up. So those are the three things you need. Those are the requirements. We have to consider the life cycle. A good number of questions about thunderstorms. They consider this a very important topic. And I want to pause here and just remind you that you're as beginning drone students, drone pilots, we often think too small, because the industry's not always going to be using consumer grade drones. If you get a job and you get involved in the industry, if you want to continue on, they're going to have to develop bigger drones. How are you going to do a delivery service with a Mavic Mini, or even the largest Mavics that you, not the largest, but there's going to have to be some development here, and that's the direction the industry appears to be going in. Right now, mapping and aerial photography is big, but there's a whole area of deliveries from drones that is opening up, and the FAA has informed us that they intend to do that. So we're going to fly bigger drones for further distances. So yeah, the whole weather issue we think really small. Like, why don't I? You're thinking, maybe, I don't know if that's true, but you may be thinking, well, I just go outside and I look around and the weather looks good, go fly. But eventually we're going to be flying further distances. And so we need to be more aware of weather. We need to understand of all these things so that we can be a little bit more of weather persons, to be able to analyze the data and do our best to predict what the conditions may be or may become within the period that your operation exists. So anyway, and the FAA recognizes that well. So you may be wondering, why are we spending so much time on weather? Well, it's not just because I like talking about weather, which I do. It's about the fact that this is going to become more useful as we develop as an industry. Besides that, your own personal information about weather is being enhanced, I hope. So the next time you decide to go to the beach, you can check the weather, and you have a lot of more tools than you used to. Looking at the Weather Channel is fine, but there's a lot more information out there available. So anyway, thunderstorms have these three stages. Cumulus stage, which is the beginning, all up, mostly updrafts. The mature stage, you have updrafts and downdrafts, because that's the point where the rain finally starts forming. The air is pushed up high enough to where it turns into rain or hail or whatever other kind of precipitation might be there, depending on other conditions. And then the dissipating stage, which the rain starts falling as well. Total life cycle of a thunderstorm is typically about 30 minutes. Now you say, no, that can't be true. Well, the conditions, when the conditions are right, we have a continual series of thunderstorms. So it's not the same thunderstorm 45 minutes later. It's just another one that started just before the first one did. But now there are steady state thunderstorms associated with some frontal conditions. It does happen. But the big thing for you to know now is that there's the three stages. The mature stage is probably the most dangerous stage, because there's a lot of turbulence in that cloud. And the very worst stage is, I think, generally agreed upon as the end of the mature stage, and the beginning of the dissipating stage is when it becomes maximum danger, turbulence, rain, all of those things. So here's an example of that whole process where they're continually building. This is not just one storm. There's three storms right here. There's a towering cumulus beginning stage, and then there's mature stage, and then there's dissipated stage, all right there. But there's more than one storm there. At least that's a better way to visualize it in your mind. Or you can call this a multi-stage. Some people will call it a multi-stage thunderstorm. That's fine. But then there's also squall line thunderstorms, which form way ahead, typically way ahead of a cold front, and there'll be just a constant line of thunderstorms, and we've talked about that before as well. Microburst associated with thunderstorms especially. We have that mature stage and then the dissipating stage where there's a lot of rainfall and it's pulling the rain down and pulling the air with it, of course. So it starts coming down, hits the ground, accelerates, hits the ground, then pushes out, and it dissipates fairly rapidly. They don't last very long either. Typically 15 minutes or less. A severe microburst, it might be called a downburst, either one, at the most. It's not very big either. It's like a mile and a couple miles in diameter, but it may have a lot of wind. It maybe have 150 miles an hour wind gusts within this microburst. So they're very dangerous, knocking trees down and damaging houses. And obviously, if you're trying to fly a drone in there, that would be a bad thing. You'll probably never see that drone again. So mostly these downbursts occur during the dissipating stage, the very ending of the stage. If you ever, I sort of enjoy sitting on my porch when there's a thunderstorm in the summer, spring, fall even, but mostly in the summer, and just sitting there in a protected space. And then during the thunderstorm, usually there's sort of a gust of cool wind that blows across me. It's like, hey, that's pretty cool. Well, that's part of what this is. Now, not every downburst or not every microburst is damaging, and they come in all different ranges. All the FAA is saying that it could be a very severe one. You don't know that. But the cold air is because that's a cold air, higher air moving down. Here's another graphic of a thunderstorm, and what they're saying is wind shear. Talking about wind shear here. Wind shear turbulence. Where's my pen? Here it is, right here, and we'll use red pen. Okay, you see the wind shear turbulence here. So as this air is being pulled up, and then air is coming down, is doing both things are happening. You have wind going in opposite directions, and that can affect your drone, the performance of your drone in a negative way. Certainly, turbulence in general is bad for any aircraft. Wind shear especially bad because the wind changes very rapidly, and if you have automation, it's not going to be able to compensate quickly. It's going to take a bit. If you're doing it manually flying, it's going to cause there's going to be a time lag between the time you can react to what's going on. There's other things going on here. There's this gust front. Again, it's partly a downburst, but not quite. Lots of you may have seen these roll cloud things before thunderstorms before and wondered what was going on. Typically we have this long overhang as well. I don't know if I have a graphic about that. Let's see, maybe I do here coming up. No, I don't think I have the graphic, but often these air currents blowing up here will end up with hail falling way down here, big hail balls falling down from the sky, causing damage. So you're out here way ahead of quite a ways away from the thunderstorm. You say, okay, I'm going to keep flying for a while longer, and next thing you know is you see the hail falling. So you may have been experienced by that. Often the hail will come down through the thunderstorm, but sometimes it happens outside the thunderstorm. But turbulence is the main point of this slide. Okay, all right. Which weather phenomena signals the beginning of the mature stage of a thunderstorm? There are a number of questions related to the stages of the thunderstorm. That's why I made a big deal about it. Anvil top is typically the dissipating stage. Not necessarily. Maximum growth rate of the clouds, not necessarily. Precipitation begins to fall. Precipitation begins to fall, and there are updrafts and downdrafts. Key feature of the cumulus stage is updraft. Precipitation begins to fall from the cloud base is the signal that a downdraft developed also, and a cell has entered the mature stage. That was the question, mature stage. Thunderstorms which generally produce the most intense hazard to aircraft are squall line thunderstorms. Non-frontal, narrow bands of active thunderstorms. The line often contains severe steady-state thunderstorms and presents the single most intense weather hazard to aircraft. Squall line thunderstorms.